Okay, good afternoon, everyone. We are here for the second webinar organized by the SAMOSAFER project, which is also part of the SAMOSAFER Online School of MSR Technology. And today we are going to discuss measurements of thermophysical properties of molten salts, thanks to the kind contribution of our colleague from the SAMOSAFER project, Dr. Ondrej Beneš, who is working at the GRC Center in Karlsruhe. So I'm going to leave the floor to Ondrej, and of course I invite all the participants to ask questions using the specific tool available within the platform that we are adopting, so that we can entertain the questions at the end of the presentation. So Ondrej, the floor is yours.
Well, thank you very much, Sandra, for kind introduction, and good afternoon, morning, evening to everyone. I'm the third speaker today, concluding this module 4, and I will speak more about experiments and how to conduct the experiments when it comes to high temperature measurements of molten salt. So what I will present today, maybe many of you, maybe majority of you are experimentalists or partial experimentalists. I'm also doing actually both experiments and thermodynamic modeling, so I'm coupling actually simulations with experiments. But what you will see is that we are using a lot of commercial facilities, such as calorimetric facilities, but we have to adopt the let's say the overall technique to handle the molten salts at high temperatures, so that we can get reliable data. So some of the techniques I will discuss throughout the presentation today are, as I said, based on commercial devices, but some are also completely or partially in-house made. So let's look at the outline of my presentation. I devoted into 4 main parts. The first one will be like kind of an introductory talk about the different fuel concepts and how molten salt reactor fuel, what are the components, and from this we take it to explain how we build the fuel mixture, how we make sure that we have we check for the purity, how we synthesize the material, and then we go towards the measurements, including the preparation, which where I will put some where I will address a couple of encapsulation techniques which are needed to keep the salts during the high temperature in a, let's say, kind of an intact state, and then towards the measurements itself. So if you start with the first chapter, the fuel concept, so there are certain requirements for molten salt reactor fuel, and they include enough solubility of actinides, because we need to have the good neutronic balance. They must be thermodynamically stable up to high temperatures. A lot of the studies that I will present also today are related to thermodynamics and are kind of validation, or if you wish, input to develop a thermodynamic database, a database that, for instance, Marcus, as the previous speaker, was speaking about in the context of thermochemical code, for instance. So they must be stable. There should be no decomposition. There should be as well stability towards radiation. Of course, there is always radiolysis when you are in an environment of high gamma or neutronic or any kind of high energy radiation typical for a nuclear reactor. But what is important here is that you have at high temperature, you operate molten salt reactor at high temperature. That the salt is molten, you are somewhere around 500, 600, 700 degrees. Of course, depends on the context, concept, whether you are in fluoride or chloride salt chemistry. But it's elevated temperature, and then the chemical recombination process is very rapid, very fast. So actually, you can compete with the radiolysis. So this is important aspect. Then you need to have low vapor pressures at those temperatures which are typical to operational temperatures of reactor. It must be compatible with certain structural materials, or in other words, you need to have a structural material that withstands the corrosion of either fluorides or chlorides, and there must be a compatibility with reprocessing technology. Again, it depends. We have different concepts. I'll come back to that on the next slide. Some are using, the traditional ones are using the processing technology to clean up the salt, taking advantage of the fact that it's molten, and taking out the fission products which have parasitic neutron capture, and put the fresh salt back. But there are also concepts which don't use this processing technology. But should you need processing technology, of course you need the salt that is compatible with it. So putting all this together, there is a limited number of metals that are suitable from the point of view of these let's say requirements. And if you look at some of the key salts which are nowadays and also historically have been studied or are considered today, we come down to what I already mentioned earlier, to two big families, either fluorides or chlorides. The molten salt reactor is also quite kind of a nuclear reactor concept, where you can really play a lot with the salt. You can also play with the spectrum. Do you want to have a thermal reactor, or you want to have an epithermal reactor, or rather fast spectrum? So this is a bit that the choice is, or the components are there to provide you with the choice of the concept. But looking at the at particular fuels which have been studied before, we have on the left side the United States historic concepts. We have the aircraft reactor experiment, which was a salt which or fuel salt which utilized sodium fluoride, zirconium fluoride solvent, so the so-called fuel matrix, into which uranium tetrafluoride was dissolved. Then this aircraft reactor experiment was followed by the so-called molten salt reactor experiment, which was a salt which used the so-called FLIVE, so that's a eutectic mixture of lithium fluoride, beryllium fluoride with enriched lithium fluoride to the isotope 7, because isotope 6, which you also can find in the nature, has natural abundance, is very it captures a lot of has high neutronic capture. So therefore you have to enrich. And this MSRE was this flight matrix-based concept with zirconium fluoride as oxygen getter, and again uranium fluoride based. And that was the ultimate concept of that era of experiments in the United States, which was the so-called molten salt breeder reactor. This remained on a paper, because then let's say the nuclear program shifted more towards sodium cooled fast reactor concept. So the MSBR remained on the paper concept, but it was quite complete concept. Again, utilized the flight as a matrix with thorium and uranium fluoride as two fertile and fissile material components. So the thorium here is the fertile material which captures a neutron during the reactor operation, and via protactinium it turns into again fissile uranium-233. So this was let's say the historical. But you can see that actually the fuel, and this is the main message, is there is always some kind of a multi-component matrix. So the fuel is not like in LWRs or PWRs when you have UO2 or MOX fuel, which is in solid solution, which is kind of a if I say it, let's say vaguely, it's a one phase of at least at the beginning of the lifetime of the reactor. But the molten salt reactor fuel is always in principle multi-component mixture. So even if you look at the nowadays concept, we have across the world different programs. In Russia, we have the so-called MOSAT concept, which is molten salt actinide recycle and transmuter. It's a fast reactor. It's a burner. It's a plutonium burner. Concept based on flight, again with plutonium trifluoride, this time dissolved. We have the Chinese concept, this thorium molten salt reactor, which is in principle very similar concept to MSBR from the past. But we have also, and this comes to the different family chlorides, we have the MECRI, so molten chloride reactor experiment, and molten chloride fast reactor. In France, they are using sodium chloride as a matrix with dissolution of plutonium chloride on the French side, and there is also uranium chloride involved in the fuel for the American concept. So you see there is quite variety of the fuel, but again the important message is that you have a multi-component mixture, different compounds mixed together, and I will say how you build the fuel, and then how you go towards the measurement. Here, a few pictures that the salt really physically is a transparent salt and with viscosity very close to water. So on the left side, up right side, you see the flight. This is from Oak Ridge, quite famous picture. So there's distillation of flight and a condensation at low temperature. And then we have a recent picture from our lab. This is actually a trial with density measurement, lithium chloride, potassium chloride detecting melt. So that's also quite transparent. So for the fuel synthesis, there are actually two steps. The first one, the main end, is the synthesis of the individual end members. So that's really the first step, and the second step is to mix them together. And of course, both steps you need some kind of a verification, a kind of checkpoint for the purity. So for the fuel synthesis, the first there are 4 or 5 steps that we normally follow before we conduct the measurement. So the first one is the fuel synthesis. So that's to produce the end members. So the end members, it can be either, let's say, you can purchase as offshore products. Those are normally the matrix components like lithium fluoride or beryllium fluoride, or if you want sodium fluoride or sodium chloride, you can purchase this from different commercial suppliers. But when it comes to actinides, this is not so trivial. There are also providers or suppliers of maybe natural uranium, natural thorium. But when it comes to plutonium, or if you want to also study equilibria with minor actinides like neptunium fluoride or even higher, yeah, you need to have in principle a lab with a nuclear licensing for that. So this is one of the things that we have actually installed at our facility at JRC Karlsruhe. So we have actually 2 lines one for fluorides, one for chlorides. And what we are doing, we are converting, we are producing the fluorides or chlorides and converting oxides. So you see on the pictures that we have actually triplet of the major actinide salts that we are using. So the first one is uranium oxide that converts into uranium fluoride. Then you have thorium oxide to thorium fluoride. You can see that uranium fluoride is kind of a green color, whereas thorium fluoride remains white, as is the oxide precursor. And for plutonium trifluoride, again, we start with plutonium dioxide, which is tetravalent, as well are the uranium and thorium oxides. Then if you want to produce plutonium trifluoride, because plutonium trifluoride is the component that we want to have in the MSR fuel, we need to also reduce it. So we first fluorinate it with HF, and then we reduce it with argon-hydrogen mixture at the elevated temperature, and we get the plutonium trifluoride. So what we are using, there are different, when it comes to fluorides, there are different fluorine media, like HF, F2, and F3 gas is quite efficient, or we have also ammonia difluoride. In our facility, we used to work with ammonia difluoride on, let's say, small size scale, but now since almost 10 years, we have this HF line installed in our labs, and we converted all the processes to HF line. And you see the glove box where this HF line is installed is on the picture with the detail of the horizontal tubular furnace, which is of course gas tight, so that the HF can stay in contact with the oxides and convert it into fluorides. So this is in principle the procedure. And for fluorides, we are using a mixture of chlorine gas with CCl4. There must be carbo chlorination. The chlorination direct doesn't work efficient. So this is those are the 2 things which we do. So that's for the synthesis. But then it comes to verification that what we produce is actually pure enough to fit the purpose of the analysis. And now, if we are looking at the fundamental or basic data on density or melting point or vapor pressures, we want to prepare as pure components or the fuel mixtures as possible. So of course, this is the goal. It's not trivial. So there are several cycles sometimes of fluorination we need to apply. But for the verification, we have kind of a standard to do a 3-fold verification every time we produce new material. The first one is the weight balance. So if you remember the slide before, when we convert oxides into fluorides, Normally this happens at temperatures between 3, 4, 500 degrees C. So there is not much of evaporation of the material. So you can verify. The first verification is the weight balance between the precursor oxide and the formed fluoride. So if this agrees at 99.5% conversion rate, we take it to the next analysis. Also, the color has to match, but color is always a bit I would be careful on saying that. But if you are supposed to produce UF4 and you don't see anything green, then you are sure you didn't convert it. So it's kind of a double check, but with care. But then when the weight balance is okay and nothing wrong observed during the fluorination or chlorination, we put that to for phase analysis by XRD. So you see this one of the examples of plutonium trifluoride. This is quite pure, or very pure plutonium trifluoride, treated with retweld analysis afterwards. For impurities, found no impurities in principle. But as many of you or all of you know, XRD is also not the most sensitive method. But it's there. It's relatively straightforward to do. So we always do the XRD. If XRD shows impurities, we know that we have to refluorinate or rechlorinate. If it shows no impurities, it still doesn't mean it's 100% pure, but it means we can proceed to the third step, which is melting point analysis by DSC. And melting point is very sensitive method to for impurities. So this is the third let's say a quality check we do on these members. And what I show you is you see the DSC output melting point determination by DSC for thorium fluoride, synthesized thorium fluoride. So you see one single peak at the right melting temperature, and this indicates that the thorium fluoride which we prepared is pure. Now for comparison, you see the last graph I show on this slide on the very left. You see this again thorium fluoride. So you see the blue curve is again single peak. Okay, I don't have the temperature, neither the time. It's not that important, but this indicates again the same kind of thing, the high purity as the middle picture shows. But then we had also not as pure thorium fluoride, which still required a conversion of residual oxygen. And you could see that there are some pre-melting or kind of eutectics formed, very likely between thorium fluoride and thorium oxyfluoride, and that causes the kind of pre-melting peak, and that's indication that there is something wrong with that, and we need to purify. So those are the three main steps. And if necessary, we also apply, but it's not always, because normally we are working with one batch and it's in argon glove boxes, all the handling, so a very pure environment. But time to time we also perform chemical analysis by ICP-MS for metallic impurities. So this is also something that we put in place. Or for instance, when we are asked by commercial contractors for quality assurance, which we have also done in recent years, we are requested to provide this ICP-MS output too. So that's the purity check. Now we have synthesized the members. We have controlled them for the purity. They passed. So then we can go to mixture preparation. Normally this is done in solid state. You take the various crystals. You know what your fuel composition is, what is the molar percentage or weight percentage, if you wish, and you mix them together. So this is a straightforward method. There is not much to really explain. The only thing is, again, I put the accent that all handling of especially open, or I would say just all open handling of salts, even at room temperature, we handle in argon glove boxes, which are connected to purifiers and constantly monitored for oxygen and water impurities, and they must be really in detail. So that also applies to non-radioactive materials, because the molten salts in general all behave like that. Some more, some less, but the protection should be in place. Okay, so then we mix. Then we make the mixture preparation of the dedicated salt, and then we verify the composition again with ICP-MS, but not for chemical impurities, but for the ratios of the matrix and fuel components. So this is done again by ICP-MS. And the fifth one, which is a bit a technique that requires also the quality check of the salt, is very often we are asked what is the oxygen content or residual oxygen content of the salts. And oxygen is a very light element, and it's very difficult to spot, to identify techniques like SEM or EDX, which we would use for higher cations. So it's not as straightforward, but very recently we have actually found maybe a very good way for future is to look for residual oxygen or oxides by measuring, evaporating completely the sample using our Knudsen cell facility. I will show this when I describe how we measure vapor pressure, so I don't have to spend that much time for that technique now. But this is that we evaporate the fuel completely, and we first see the evaporation of the main fluoride, in this case fluoride components. And if there is still some residual oxygen, it will we will see it afterwards, because this technique goes almost up to 3000 Kelvin. It's in an ultra high vacuum, so we can evaporate also oxide fuel samples in principles completely. So we actually can scan all the chemistry by evaporating completely the sample. So this is something that is newly implemented. So this shows you also what we did in practice. So this was a fuel synthesis. So actually that kind of sums the whole procedure I was explaining now. This was a very recent and very extensive campaign to produce about 100 grams of a fuel mixture for irradiation. The irradiation is done at NRG pattern in a high flux reactor. So this was a collaboration between NRG pattern and the JRC. And we were asked to produce the fuel. The fuel was a mixture of lithium, thorium, uranium, plutonium fluoride. We had in total 5 capsules that go to the reactor. And we are also looking at not just the performance of the fuel during the irradiation, but we are also looking at different corrosion rates versus different materials when we control or not control the redox potential. So the redox potential, I wasn't there when Sylvie explained her talk, but I'm certain she spoke somewhere about controlling redox potential of salt. So in this case, it's done via this pair of uranium-4 and uranium-3. So we had one salt which had only UF4, and then another one the same, but with addition of 10 equipercent towards the UF4, so 10% of uranium trifluoride to decrease the let's say the fluorine potential, the aggressiveness in principle, the corrosiveness of the salt. So we will have this benchmark. So this was, we were asked to prepare like 5 different capsules. The capsule you see, that's just a scheme around here. Each capsule takes something like 8 grams of fuel. So although we prepare 100 grams, only 40 grams or 45 grams go to the reactor. There were also capsules that do out of pile benchmarking tests, so that's why it sums up to almost 100 grams. And you can see that we did all the analysis, XRD, we did the melting point, we also did the melting point determination of the fuel mixture afterwards. And you see one of the frozen ingot of the fuel. So you see the typical color of this nice light green, which is let's say domain of uranium tetrafluoride. So this was done, and that actually was one of the major campaign that actually kind of addresses all the steps that I was explaining on slides before. So that was about the fuel synthesis and the verification. Now we go to the chapter 3. This is about the that's when we have the fuel mixture, we want to measure different properties. So before we do that, there must be also some careful handling of the salt. So I already mentioned before that open salts should be treated in argon dry boxes so that we prevent oxidation or moisture absorption, which result into some oxides or oxyfluorides or hydrates, so that you want to avoid, because you want to really just focus on halides. But this also applies, the careful handling applies also to high temperature experiments. So why is this? Because the salts, they have low vapor pressures, but that's not zero. They are at elevated temperatures. If you go to melting point and beyond melting point, you can go sometimes even a couple of hundreds of degrees higher than even your operating temperature of reactor, because you want to also study the properties of the fuel during accidental conditions. So you need to avoid this vaporization during the measurement for 2 reasons. or maybe even 3. So first one is you don't want to lose the sample during the measurement. If you have enough sample, that wouldn't be that huge problem as long as you don't do quantitative analysis. But it is a problem because you may corrode your instrument at those high temperatures and you destroy it, and then that's certainly a economical issue, and also it delays things for future. But second, it's a multi-component mixture, and each of the component of salt evaporates differently. One mixture component evaporates more, the other less, so-called incongruent vaporization, typical for most of the compositions we will ever examine. And this, during the measurement, could lead to different composition than you actually nominally want to look at. So, of course, this would open a lot of room for errors. So you want to avoid it. So you have to encapsulate the samples if you measure most of the properties. Of course, if you look for vapor pressures, you cannot encapsulate the sample because then it doesn't evaporate. But those are unique examples where you not have encapsulation, but when it comes to melting points, heat capacities, transition enthalpies, etc., you should certainly encapsulate your samples. Then the encapsulation, it's not that trivial, but why? Because you need to contain the liquid also, and you need to find a material that that is compatible, chemically compatible with the salt. So normally we are limited to nickel-based or even nickel-pure metals. Carbon is like graphite is very inert. Boron nitride is also a very good material, but it must be oxygen binder free, so it must be oxygen free boron nitride. So then important is that the encapsulation fits the purpose. So we at JRC have developed a different encapsulation techniques also to be a bit on the practical side. So the first one is relatively straightforward design. It's a stainless steel a crucible, where we have it's a robust body, and we put a liner from inert material versus towards the salt. So this liner can be boron nitride, graphite, or nickel, and only into that liner we put the salt that we want to examine. So the whole crucible, the stainless steel, is there to hold the robustness. So when you put it, for instance, in a relatively fragile ceramic compartment of the calorimeter, you know that at high temperature it will not deform. If it was from pure nickel, nickel is relatively soft material, you could have deformation that would lead to have the crucible finally stuck in the detector, and that cause damages. So we have the stainless steel that for the robustness, but the liner for the chemistry, and we have also nickel seal on the top, which is squeezed by solid bolt, and straight edges of also made out of stainless steel. It's just circled here in the middle, and it's squeezed by the bolting system, so it's hermetically closed. It's tested up to 250 degrees long term, so really even weeks. And the good thing is that this what you see on the picture, it fits exactly the calorimeter. It's used, as you will see on different slides, to measure melting points, transition enthalpies, etc. But it's due to the robustness, it's only good for qualitative analysis, and not much for heat capacity. Heat capacity, that's very, you need to have a big sample versus crucible ratio, and this design does not provide it. But what is nice that when you have this design, it's also relatively sizable. So another purpose that you can use such a crucible that actually encapsulates the salts is to, and I mentioned this already, is for instance to produce fluorides in a very large scale. If you don't have an HF line or fluorination line, you can actually use this ammonia hydrogen difluoride, put it with oxide within this big crucible. It is robust, it's hermetically closed. You heat it up, the ammonia hydrogen difluoride decomposes into the various components. So HF, which is the fluorinating agent, H2, nitrogen, and ammonia. And with these conditions, you have also quite nice reductive conditions to convert directly plutonium dioxide and plutonium trifluoride. And this was also one of the early cases we were using in our lab. Before, again, repeat, we had this HFO. So this is limited to few hundreds of milligrams, but it's better than nothing. So let's do the first type of encapsulation, and the other type of encapsulation that we are using, or different labs around the world are using, is based on laser welding. So we have this quite high power laser. We put this. We have different sizes of crucibles, but you can really play even with the pure nickel material. It's very simple cylindrical design. You put a pressed pellet of your fuel into or of your sample into the crucible. You close it with the lid. And you just press it together. And while rotating, you should laser on the edge on the top, and then by rotating it, you close it. There is always a bit. It's very tiny crucible. Now we do it because here we want to use these kind of crucibles, for instance, for quantitative analysis of heat capacity, for instance, as I will show later. And there really the demand on a lot of sample but little crucible material is needed. So that's why also let's say the walls are I think 0.2 millimeter thick, so that we have really this ratio of sample versus encapsulated material as high as achievable in principle. So this is another type of encapsulation that we are using. Important is, after we encapsulate the material, to test it. The best is to heat it for several hours at high temperature and compare the weight before and after. And that gives us really idea whether it evaporates or not, because if you go as high as 1200 degrees, for instance, you are sure that if there is leakage, it will decrease the weight. So let's go now to the experiments. I think I have still some like 15, maybe 15, 17 minutes, so I think that should cover. So I'll show now we have encapsulation done, we have pure samples from the synthesis, then the mixture preparation. So now I will go through some examples, what properties are relevant for us. And this also gives us a bit bridge between the presentations we had before, and particularly what Marcus was saying about different thermochemistry and also multiphysics scope. So when we look at from the reactor concept perspective, the thermophysical properties that are of concern are, I mean, there are several, maybe even more than on this list, but let's say the ones I like to mention are the melting point, heat capacity, vapor pressure, solubility of actinides, that's more or less the liquidus barrier, then chemical stability to high temperature, but also kind of transport properties like viscosity, thermoconductivity, not of course also density. Now, if you look at many of these properties and the first five, they are all linked to this, what Marcus was saying also in equations, the Gibbs energy or thermochemistry. So if you can address, if you have a model, thermodynamic model of a fuel system, you can address all these five properties. And it goes also vice versa, that to make the thermodynamic model, you need input of these properties. So this is also very important message I want to share, that there is no, let's say, robust thermodynamic model if you don't have a solid data set, experimental data set. And I will show a very simple example on my next slide. So this part of the properties is related to the thermochemistry. Marcus mentioned, already announced, we have this what is called JRCMSD, so quite extensive thermodynamic database describing in principle all fuel concepts, even on my second slide, which I showed different, I think 6 concepts. So they are all described by this database. Of course, it can be improved with new data. We are working on it, but it already provides quite a good description. And then we have different chemical softwares that actually can read the database and provide the relevant calculations via this Gibbs energy minimizer. I have a snapshot of FactSage. I'm using FactSage. It's a commercial software, but Marcus has been extremely busy to do the tremendous job to develop this Thermochemica, which will be open source. And that is important because that allows to couple the thermochemistry with multiphysics. And multiphysics is then kind of like the flow, the studies of the flow simulations, where you need also properties as well, heat capacity, but viscosity, and thermoconductivity and density. So if you can couple these two, let's say, simulation tools, you can very well describe and predict what is going on in your reactor. And for this, as I said, the input of experimental data is needed. as well when you simulate something for the validation. It's also extremely important. I think I would not be wrong if I say that license-wise, you always need to confirm by experiment that it is like you think it is. So that is the small example of how experimental input is linked to the or one of the experimental input is linked to the model. So what we are looking at is the simple binary, pseudo-binary system between lithium fluoride plutonium trifluoride system. This has been modeled in the past. It's one of the phase diagram part of the nuclear database on a thermochemical database. You see it's simple eutectic system with eutectic somewhere around 22 or 21% of plutonium trifluoride in molar percentage, so in the molar composition. And what is the link between the experiment and the model is highlighted here. So the points are so you have open symbols and closed symbols. So open symbols are data from Oak Ridge, that's Barton data, and the open symbols are what we have recently measured at JRC, though they match pretty well, and they suggest this simple eutectic. So we measure systematically at 5 molar percent or 7 molar percent a step. This depends on, of course, whether the system is more complex or less complex. Sometimes we need, let's say, more precise composition step. But for this system, it was enough to give the general ID, and then the model provides you the line. So without this experimental input, we wouldn't know how to where the liquidus line should go, what the slope should be, etc. So this is very simple example to show you that the experimental input helps to provide robust thermodynamic model. Now, if you have several of these binary systems, you build them together, you can extrapolate higher order systems. In this case, it's an example of lithium thorium plutonium trifluoride system. One of the key system of this firm, molten salt fast reactor, the fluoride salt reactor that is studied, but has been studied in the past mainly by CNRS, but in collaboration throughout European projects too. So this was one of the output of the study. So when we put all three binary systems together, we can extrapolate what we are looking at is liquidus projection and look for the lowest melting points, so-called regions which have particular interest to molten salt reactor community. So why I show this? Because from small systems you can extrapolate higher systems, typical for molten salt reactor fuel. But again, when you have such extrapolation, you need to validate. So then you take a few points and measure whether the liquidus point is in line with the model or whether we need to re-optimize. So this is kind of important to always have in back of mind. So let's go to properties. So the first one, melting point. I've already mentioned the encapsulation. The technique for melting point, what we are using, and I think most of us would agree with me that the differential scanning calorimetry or differential thermal analysis, DTA or DSC, are probably the most used around the world to look at these high temperature melting points. So again, I take the liberty to repeat the example from a slide before. Again, lithium fluoride plutonium trifluoride system, but in this case, I want to correlate it with the output. So this was the measurement of this 20% molar percent composition, and you see only one single peak here, which indicates that that's really the true eutectic, because you see no other peaks which would relate to another phase equilibrium. Something a bit different situation is when you move the composition towards 23% or 24 molar percent, you already see the eutectic peak, and then you see also another peak which is related in this case to liquidus temperature, and this is exactly the second point here on the graph. So if you then do this for different compositions, you identify these two critical temperatures, onset and offset in this case, and you get a nice view or ID of the phase diagram. So this was the first property. The other property, this is more for the quantification, is you can not just measure melting point. What we are looking here is again the differential DSC output. This was a mixture of 78 molar percent lithium and 22% thorium fluoride. So the eutectic mixture of this lithium thorium fluoride system. And again, we observed this single peak that corresponds to really the eutectic composition. So you can as well identify the melting point. But what we did in this campaign is we were using also internal standard in the other crucible. So DSC has always two crucibles. One, then you have the sample, and the other crucible, which is called reference. Normally it's kept open. But with this test, we put silver reference material into the reference crucible to quantify the heat flow that we are actually measuring between the two crucibles, and that is proportional to the total heat effect. So from that calibration, from that internal reference, we could get this calibration factor and apply it to the salt, and we could not just get the melting point, but also the enthalpy value for fusion, which is also extremely important for the reactor designers, but also for the people that actually do the modeling part. So there is some benchmarking, and you see that as three different sources provide a very good match, especially when you also take into account the uncertainty, which needs to be taken into account in every measure. The third one with DSC is the so-called mixing enthalpy. Now, going a bit to the why mixing enthalpy is important. This is important. So mixing enthalpy, in this case, what I demonstrate here is for the liquid solution between lithium fluoride and thorium fluoride. Again, it is kind of a reference to the stability of system, and it's linked to the Gibbs energy of the liquid. So if you have two component liquids, or lithium fluoride, thorium fluoride in this case, the main part of the Gibbs energy comes from the members itself at given temperature. But then there is also this mixing part, which is again mixing enthalpy, mixing entropy. So already, if you can address the mixing enthalpy, it provides you big steps towards a good description of the overall Gibbs energy function of the liquid solution. So what we have done, we have put a palette of pure thorium fluoride and below of pure lithium fluoride. We put it in this crucible we are using, again everything encapsulated, and we put a nickel separator between. Now what happens when lithium fluoride melts? It separates things, thorium fluoride gets in contact, and upon melting point of lithium fluoride, we are measuring actually three effects: the fusion enthalpy of lithium fluoride, also the fusion enthalpy of thorium fluoride, because it will eventually also turn into liquid. But there is also this delta H mixing, which is then the third component. So if we subtract the fusion enthalpy of thorium fluoride and lithium fluoride, we can get enthalpy of mixing of this particular composition that corresponds to the ratio between the two bulk materials. Why is this important? This is the outcome which we got. Okay, sorry for the blurriness. I have certainly a better picture, but I couldn't find yesterday when I did the presentation. So it's migrating between office and home office. So this is unfortunately what I got, but I think it gives you already the idea. So these are the values we got with uncertainty. And what is interesting here to see that, for instance, we have already modeled this lithium fluoride, thorium fluoride system in terms of thermodynamic description in the past, and we got mixing enthalpy which corresponded to this curve, and for different temperatures. So of course it's unique for temperature if it's temperature dependent. But with the data we measured, we had to improve it, and you see that the improvement is quite substantial. So it shows that even these mixing enthalpies are extremely important when you really want to improve the database, so that you can provide more and more reliable estimates. So that was for the DSC for transition equilibria. We are also utilizing the DSC for heat capacity measurements. I told you earlier when I was dealing with the encapsulation that these robust crucibles cannot be used for heat capacity measurement because they are too big and you put just too little sample inside, and the heat capacity measurement is quite sensitive for this ratio. So we are actually using these crucibles with the laser welding, where the ratio is shifted towards the sample. It needs some patience, but finally you can get quite good data. What we show here is the step method. This was measurement of thorium fluoride, but the principle is same when you are using the same approach. We were using 100 Kelvin step, assuming that in this 100 Kelvin the heat capacity is principle constant, so we took the mean value, and we heat up the sample. And if we do 3 consecutive measurements exactly with the same conditions, only different crucible, so one is blank measurement for the background, the other one reference to get the ratio between the peak that we measure while heating stepwise the apparatus by 100 Kelvin. So we get this calibration, and then when we measure sample, apply this calibration. Of course, both calibration, the reference material and sample must be subtracted by the blank. We get the heat capacity. So this was a measurement, and then we got the heat capacity for before melting, for high temperature solid, but also for the liquid phase thorium fluoride. So that's to the principle. And another method which we use as a benchmarking method to look at the heat capacity is again calorimetric method, but in this case it's drop calorimetry, not the DSC. And the principle is based that you are dropping a sample from room temperature into the hot furnace, and you are measuring the enthalpy increment. So it's not direct measurement of heat capacity, as in the previous case, but it's the enthalpy measurement. But then if you derive enthalpy with respect to temperature, so if you do these drops, it's isothermal method. So if you do a one day one temperature, another day another temperature with several drops, as shown here on this graph, you get enthalpy as function of temperature, and the derivative with respect to temperature gives you the heat capacity. And again, here we are using these small nickel crucibles with sample inside. Again, increase uncertainty because you have to always subtract the contribution of the nickel, but it's the best we can do for this method. Now another graph shows you again output of drop calorimetry, but in this case with results. So this was another campaign we did 12 years ago. Was for looking at cesium fluoride as one of the fission product form. So we kind of reviewed the experimental data. So we made the measurement of solid phase, then we had the fusion, so the melting, and then we measured the liquid phase. So already this graph also shows you a bit the uncertainty, relatively high, but if you do more points, you can get quite a reasonable fit. So it gives you, it provides you the enthalpy fit for the solid and liquid phase. So again, the derivative gives you the heat capacity, which is then highlighted here for solid and liquid phase. And what it also gives you, it's another method, or benchmarking method, to a different type of approach to measure the enthalpy of fusion, because I told you we are measuring for solid enthalpy, for liquid enthalpy. So at the melting point, the difference is the corresponding to the fusion enthalpy. So this is something that we obtained from this measurement, 21.6 kilojoules per mole. And if we compare this with the DSC, which we measured in independent measurement using this internal reference, we got 22.2. So you see that it's a very nice match. And this is also something I want to highlight, that if it comes to quality assurance, it's not a mistake. It's sometimes even very welcome or must to have two independent techniques, or even two independent labs to look at one property, so that maybe licensing authorities can consider that for the reactor design studies. So this is why we sometimes look at two different techniques. Now, almost coming to the end, but give me some words still about the what time is it? We have still maybe 5 minutes, so that's about for the Knudsen cell. So this is to I promised you that I mentioned this method looking at these residual oxides, should they be or not in the sample when speaking about the purity check. We are primarily using this to measure to look at vapor pressures or even boiling temperatures of the fuel. The method is based, we have this so-called Knudsen cell. Normally it's a tungsten crucible with very small orifice on the top. You put your sample inside, so the scheme is here. You put your sample inside and you constantly heat the furnace or the crucible. If you wish constant heating rate, typically 10 Kelvin per minute. And the higher temperature, the more volatile it gets. And then when it evaporates, it goes to ionizing chamber, and then it's sent to the mass spectrometer. So you are measuring different masses, and each mass corresponds to different to unique species. There are some dissociation processes involved. Let's not speak about that. It's a big nightmare sometimes to evaluate the data. But from the masses, we can get to the species that are in equilibrium in a gas phase with the condensed phase. And then what we determine are the partial vapor pressure. So again, multi-component system is the fuel. So if you have lithium, beryllium, uranium, thorium, we can detect all four in terms of partial vapor pressure. So for instance, here we have different partial vapor pressures of lithium, thorium, uranium, plutonium, fluoride fuel metrics. And from, let's say, some of these signals, you can also extrapolate the boiling point. We can never reach boiling point because we are in ultra high vacuum. So before we reach boiling, the sample is gone. But but the extrapolation methods are work pretty well, and we could determine with some precision uncertainty also the boiling. So this was actually the scrap of the fuel. You saw it already earlier. This is another example. Again, the same thing, using Knudsen cell facility to measure vapor pressures. In this case, it was a systematic investigation of lithium fluoride, thorium fluoride system. We had 4 intermediate compositions, 20, 40, 60, 80% molar, vice versa, lithium, thorium. And we were looking actually at the vapor pressure of lithium and thorium fluoride, so lithium on the right side, thorium on the left side, how it develops with the composition. So this was also extremely important because it provides you the activity determination as function of composition and as well as temperature for the 2 lithium and thorium fluoride and members. It's a typical input you need also for thermodynamic modeling. And last example on the Knudsen cell, and this is something that goes a bit beyond than just fundamental properties. This is already extending the knowledge of the fuel behavior when it starts to contain, let's say, fission products in this case. This is something also I've been a lot of focusing on. Okay, the principles are the same, but I was focusing in my talk mainly on the fresh fuel, let's say, fuel compositions. But of course, for the reactor design, it's also important to know what is actually happening with the fuel and thus also with its properties with respect to the operational lifetime of the reactor when you accumulate fission products or even maybe corrosion products. So that's also something that we are focusing on now. I told you, for instance, the database that we always correlate our experiments with describes pretty well the fuels, the fresh fuel systems, but we need to add more and more now the different fission products, corrosion products, also to address how these how the fuel properties develop with additions of these two groups, so fission products or corrosion products. So this was one of the examples, but it was also kind of let's say a pioneering study to reveal how it's with fission products with this size, cesium fluoride, with this cesium iodide. So we were focusing at the major volatiles here, at the cesium and iodide. And in the first step, we wanted to know what would be the most probable cesium and iodine forms in a molten salt reactor fuel. Of course, the best is to take irradiated fuel, if you have irradiated fuel, and measure the irradiated fuel. But if you don't have yet irradiated fuel, you want to do these syn fuel mixtures. So in the first step, we actually identified that with the fluorine potential, when you have the predominance phase diagram, this is the fluorine potential axis. This is iodine is also a volatile component, so this is iodine axis. So if you add cesium as the central metal, you can determine your fluorine potential determined by set by the ratio of UF4, UF3, which is typical for molten salt reactor, and take operating temperature 900 Kelvin, for instance, and we identify that if we let's say limit our window of fluorine potential likely to be in the reactor, and plot it with respect to the iodine pressure, which can be high, low, depends on how the fission goes. We have in principle 2 forms, cesium iodide and cesium fluoride. So therefore, we took these 2 forms, we mixed it with the fuel. In this case, it was lithium fluoride, thorium fluoride matrix. And we measured by this Knudsen cell, so with pressure measurement, the fuel with cesium fluoride only, and then the fuel with cesium iodide. Now, with the cesium fluoride, it's a bit mess here. It must be like that, but let's not go to each of the curve. But what we have seen, so if you see my mouse, these are reference values for cesium fluoride. So that's the 3 different sources more or less matched together. This would be the vapor pressure relatively high of pure cesium fluoride. Now, what happens is when you put it, this was 1 molar % of cesium fluoride in lithium thorium matrix. If you dissolve it in lithium thorium, you clearly see that the cesium fluoride, which is this blue curve, is by almost 3 orders of magnitude lower. So this really confirmed that the cesium fluoride has huge retention by the fluoride-based fuel. And it will be very, the volatility will be super suppressed. This is something that people were expecting, but this is the more or less the first clear experimental proof that it's really like that. Now, if you look at the cesium iodide, it's a bit different because again here you have the two, in this case, two reference values for cesium iodide. It's more or less comparable to cesium fluoride, a bit more volatile, but not like tremendously more volatile. So it has some volatility. And if you look at the cesium fluoride, the cesium iodide, which was supposed to be dissolved, you see that when you heat it up, it's not dissolved at all, and it kind of has the impression that before the cesium iodide is evaporated out again, this was only 1 molar percent of cesium iodide mixed with lithium thorium. So it tends to come more or less with the volatility towards the baseline value, towards the high volatility. We have repeated these experiments. We have done also some melting encapsulation experiments as part of this campaign to see whether the cesium iodide may be not dissolved at low temperature, but dissolved at high temperature, but really not. It is still, it showed that really the miscibility of cesium iodide towards the fluoride-based matrix is quite high, and it showed that the cesium iodide, it has quite a different behavior compared to cesium fluoride. Nevertheless, still the conclusion of this study was that although cesium fluoride is really suppressed by its volatility by the matrix, cesium iodide is far less, so it is quite volatile. But still, if you compare cesium iodide volatility with cesium and iodine element, which may be formed in oxide, solid oxide fuels, it is still a couple of thousand times lower volatility. But if it was even dissolved, it would be even more, as is the case of cesium fluoride. So it was a quite interesting result of this, looking at fission product behavior. I think I'm out of the time. Density Archimedean method, it is under development. Maybe I can speak about it when we later on, when we have also some results on actinides. So far, we are testing at towards high temperature with inactive mixtures, all down in a glove box, again because of argon atmosphere. It is still, you can see, it's the prototype. The principle is based on submerging the nickel bulb into the molten salt and measuring the buoyancy effect, of course corrected to surface effects of the wire. But the results are fairly good. We measured fly neck, lithium, calcium chloride, eutectic. Now we measured 3 compositions of lithium chloride, cerium chloride as surrogate to plutonium chloride at later stage, and get very good and reliable results. So that was the one before last, and the very last is thermoconductivity. Thermoconductivity is measured by laser flash technique. Laser flash technique is based on, normally we use this technique to measure solid oxide pellets. You see that this is also kind of in a semi-hot cell. So we are also using this to examine as part of PIE, so irradiated oxide fuel pellets. So we put the pellet at certain temperature at which we want to determine the thermoconductivity or first diffusivity. And then we shoot the laser, short pulse laser on one side, and we measure with pyrometers the temperature response with respect to time of the error, and that's proportional to thermodiffusivity, providing you know the porosity, and then if you know heat capacity and density, you can get thermoconductivity. So this technique we also utilize to measure the thermoconductivity of molten salts. This is still under development, but we already have had some preliminary results, as you see on this graph, for lithium fluoride, also solid and liquid, for fly neck salt, for even plutonium trifluoride. The difficulty here is, again, the encapsulation. You have to have a crucible that fits the purpose of the measurement. So in this case, it's a modified crucible where you measure the thermoconductivity only between these two plates. So there is maybe a 0.5 millimeter or 1 millimeter. We have different designs. So here in this concept is 0.5 millimeter gap, and then you shoot a laser on one side, the heat penetrates, and you measure the temperature response on the other one. It doesn't go as straightforward as with the when you measure only the oxide puck or oxide pellet, because what we observe, and that's the crucial problem, is when you make X-ray of the crucible. So here you see a bit more shady area. That is the salt, is molten, and sometimes if you look at the top, the XRD from the top, you see small like cavity, small bubbles, and then if you have a bubble in this area, that completely spoils the experiment. So we have to tune up, optimize the process. But yeah, when it goes well, we can measure very good the thermoconductivity, but it's not reliable in a reliable state yet because there is still a random factor of creating these bubbles. But it's very promising. But it gives you an idea how the technique works. So conclusions, only two. Make sure when you measure the sample that it's of appropriate quality that fits the purpose, and then make sure that you conduct the measurement and you get what you intend to get. Should it involve encapsulation of that or another type, it must all fit the purpose. So with that, I stop and I thank you for your kind attention.